I'm Karthik. I'm a solution architect in the HPC space at ExxonMobil Technical Computing Company. I am representing my co-authors here, Kirsten Byers, Rahul Sampath, Raj, Ronaldo, Jordan, and Jeremy, most of who are in this hall. And I'd also like to thank this big audience here who's gathered to listen to my talk, even when Gary from Los Alamos is presenting in the other place. So it's a privilege. Thank you all. So, no pressure, though. Yes, it is a lot of pressure that I'm competing with Gary, but whatever. ExxonMobil is not new to HPC. We've had HPC for many, many years, and somewhere recently, I actually saw a document which made me realize that ExxonMobil has been using HPC for longer than I've been alive here. So this work is not just my work or my co-authors' work. It's a representation of the generations of HPC engineers who've worked at ExxonMobil, the ones who have introduced this method of benchmarking and acquiring new supercomputers, which have been iteratively improved, and we've kind of standardized that now, and it's a well-oiled machine, so we don't really go and reinvent the wheel with benchmarking. We just keep doing what our ancestors have done, and I'm just presenting it to the world today. So what am I going to talk about? First, I'm going to talk a little about what do we do with HPC at ExxonMobil. You might have seen glimpses of this in other presentations at other conferences. It's pretty much similar to what other oil and gas industries do, but I'd still speak about what do we do with HPC. I'll talk a little about how do we design our next generation hardware. And a caveat here is when I say next generation hardware, it doesn't just mean the on-prem when we are benchmarking. We are benchmarking hardware that can be available at any platform. So we do not have a bias on whether we want to be on-prem or on cloud. There are reasons for why we are what we are today, but it doesn't mean that we have a platform of choice. We are always open to be wherever, whichever helps our business the most. And as I'm talking about how do we design our hardware, I'm going to talk about the methods that we have kind of used over generations to acquire new machines, look at new platforms, and what are the different considerations that we have while we make these decisions. It's not one or two constraints that we have. There are multiple considerations. Some of them are more important in one purchase. Some others become more important in another purchase. So it's always dynamic, and I'm going to tell you a little about how do we decide what is more important for us. I began this presentation by saying that we are not new to HPC. We've been doing HPC for a very long time, and we have a lot of different customers within ExxonMobil who use the HPC. And without a lot of doubt, upstream is our biggest customer. Geoscience is where we find maximum use cases. But that's been changing. We are starting to see a lot of interesting applications for HPC outside of the upstream business in chemicals, in facilities. There's a little bit of research happening in molecular dynamics, in quantum modeling, etc. So HPC is actually being used outside of upstream as well. But this is a chart that our team likes to keep, and this is something we had in 2022. This has changed considerably in 2024. But the theme doesn't change. Even in 2024, I would say seismic is our biggest user of the HPC. We have multiple machines, platforms where we run the HPC. The largest machines are all designed for seismic. So this story, the rest of the story is all going to be on the basis of seismic. And that's why I said thanks to Rice for the way they've organized this sessions today, because a lot of seismic talk has happened. So maybe I can preempt a little less compared to what I thought I would have to speak. So let's get into the meat of this. I've been fascinated by supercomputers for a very long time, but before I came into the industry, I believed that supercomputers are a bunch of interconnected machines. They can solve any problem, and they can solve these problems at lightning speed. After I came into the industry, I realized that I was partially correct. Interconnected machines, yes. They can solve problems at lightning speeds, maybe, if you design it well and if you write good software. But they are not general purpose machines. Most of the supercomputers are not meant to solve each and every problem. Every supercomputer, every high-performance chip, which is on any platform, is specifically designed for certain problems. And it's very important that we put in a little bit of thought into designing the hardware for the kinds of problems that you're trying to solve. In our case, the largest machines that we build them for seismic. So it's important for us to benchmark any hardware, any platform that we consider for HPC by keeping seismic in mind. So our methodology is around designing these machines specifically for seismic. These machines might not be great at doing other problems, but we want them to be super fast when we are solving seismic problems. So that is our benchmarking strategy. Since I'm talking about seismic, and this is where I have to thank Professor Biondi for what he presented in the morning, someone of his reputation talking about this gave me a lot of confidence that the slide that I've put here is not wrong. It's kind of correct. So I'm going to give you a moment to look at this and digest it a little. On the y-axis, I have pre-compute capacity, which is in teraflops. On the x-axis, I have years and a little bit of prediction. Don't quote me here. This is a simple linear regression model that I ran and did some kind of estimations here. It might be wrong. The compute landscape might change a lot. The message I want you all to take from this particular slide is the evolution of the supercomputing space and the evolution of technologies that have been used in seismic imaging. So as supercomputers have become more and more fast, we have actually enabled better and more accurate methods. The methods have always existed, as Professor said. It's only now that these methods are being able to be run on these giant machines. So the exascale project, the exascale could be, I think, the third from the top. That's the exascale. The exascale project, when that has actually enabled the full physics-based wave equation solvers that we have. The RTMs, the FWIs of the world, they are trying to solve the wave equation, and we are trying to solve it with as much physics information as possible. We've always known the math for it. The math for it has been known for a long time. But it is only now, when supercomputers have reached that compute capacity, that we are able to truly do that. And there is interest at ExxonMobil to try to solve the wave equation as much accurately as possible, like pretty much everybody else in the industry. So it is only fair that we keep getting our research folks and processing folks newer and newer machines periodically. So we keep doing benchmarking regularly. Even when we are probably not in a purchase window, we keep doing benchmarking just to understand if there is a hardware out there that can solve a problem that cannot be solved today. And then we probably go to the business and we say that, you know what, maybe it's time for us to do a refresh on our compute because it's going to enable newer technologies, and hence, it's going to probably enable us to do fun things. This is a slide that's, what I'm going to talk about in this whole talk. I'm going to talk about the methods that we have for benchmarking, and then I'm going to talk about a bunch of considerations that are important for us and how each of the considerations are different in each purchase cycle. To begin with, as I said, we are really interested in the wave equation-based seismic imaging, and I'm pretty sure this overview has been covered multiple times in this, in this conference already. So, very simple. We are trying to do the wave equation simulations. We do a forward propagation, backward propagation, and we do imaging and gradient using cross correlation. So our problem is compute dominant. We need really powerful compute. We need a lot of storage, as was mentioned in the previous talk. When we are doing RTM, FWI type of methods, we need to store snapshots, so we need a lot of memory. And then we're doing fine-grained parallelism, which means we actually we can process shots in one node or maybe two nodes. So we don't need these giant 72 node racks that the AI workloads need. So that's the kind of machine that we want to develop. So in order to develop machines that can excel at solving these problems, we have a standard procedure that we follow. So first thing is we try to identify the best hardware out there. And for that, we do benchmarking process. And we do this benchmarking regularly. We are always in the lookout for hardware, integrators, platforms, which can give us the best performance on the kinds of applications that we want to run. It is the data that comes from this benchmarking exercise which goes into informing any purchase decision. Sometimes we make a decision to purchase a machine and we do a benchmarking study closer to that. Other times we would be doing a benchmarking and we would have come across something that's very interesting and we go and inform the business that maybe it's time to do a purchase. So our purchase decisions are almost always, in fact, it's always data-driven, and the benchmarking exercise is what feeds into our informing our purchase decisions. Agile. We are big believers in Agile. Our team has been doing Agile for close to a decade now. And we do Agile even when we are doing the benchmarking process. So in order to respond to uncertainties, in order to time box activities, in order to keep shifting priorities, the benchmarking activities always happen in an agile software development kind of a way where we keep our stakeholders informed about everything that is happening in the benchmarking journey. It's not a black box to people. It's not a pet project. These are projects which are prioritized, and there is a lot of value that our organization sees in doing the benchmarking activities in an agile way. So agile is very important to us, and we apply it even to the benchmarking project. And here comes the thing that we really are proud of, and this is something that we've developed over generations, and we've implemented them, we've improved them, and we've kind of standardized them. Our simulators are giant. They have about 400,000 lines of code last that I saw it. We cannot take these 400,000 lines of code and benchmark them on each and every platform that is available for two reasons. One, it contains almost all of our IP, so it is impossible for us to share this with vendors. Two, it's going to probably take us years, months, if not years, to get this compiled, running, optimized on each and every hardware. So we are not going to take our simulators and run them on each and every new hardware that is available. If we were to take our simulators and run them on each and every new hardware that is available, we are not doing continuous benchmarking. It's impossible for us to do continuous benchmarking. Since we want to do continuous benchmarking, we have created a list of representative workloads, which we call them as mini apps, and this is not an ExxonMobil creation. This is something that is standard in the industry. Everybody calls them mini apps. We are very proud of our mini apps. Why do we have these mini apps? Well, one of the reasons is what I said, but there are more reasons to it. So our seismic imaging application, the engine of it, has about 1,800 files excluding dependencies. Many dependencies. There are a lot of dependencies on our seismic imaging applications. 400,000 lines of C, C++ code. Now you can add CUDA also to it because we have a GPU machine. So it's CUDA code as well. Lots of dependencies. We have a complex build system. So replicating this build system on each and every new hardware is not easy for us. And as I said, one, we cannot share it with our vendors. Even if we share it with our vendors, they are probably not going to want to port and build this application just for the sake of benchmarking. It's going to be quite an arduous task for them, and they're not going to want to do it. So what we've created is we've created a lot of mini apps, not one, but we have many mini apps, and people who've worked with us, they call these mini apps as mini app 1, mini app 2, mini app 9, mini app 10. They kind of know which mini app are we interested in a particular benchmarking exercise and why, and they have a number, and that's how popular our mini apps are. So each mini app, well, I call them a stencil file, but they can be more than stencils, and I'm going to quickly come to that. Each of them is a single file, independent of everything else. MPI is the only kind of dependency. We are an MPI shop. We do have OpenMP as well, but in the mini apps, we're trying to look for MPI. So our mini apps are mostly like single lines, small files, MPI being the only dependency, no IP in it. We have extracted the IP out of it. So we have two kinds of mini apps. We have one mini app which just checks for the compute, the storage, the network speeds. It's gibberish. The math is all wrong intentionally. And only after it passes this litmus test of whether your compute is fast enough, whether your interconnect is fast enough, etc., we go to the second set of mini apps which are mathematically correct. And this we probably won't share with all of our vendors. This is when we get involved, and then we probably want to get access to the hardware, and we run it ourselves. So the mini apps that we give our vendors is gibberish math. It would not be the right math at all. So we're not looking at accuracy when we share mini apps. I can see a couple of nods from people who've gone through this exercise with us. All right, so an important aspect for us is to understand which mini app is important for us in which benchmarking, in which purchase cycle or when we are doing benchmarking. So I'm going to quickly show you an animation of what happens in a forward simulation. So in memory, we have a bunch of models and wave fields. These models and wave field get injected into a stencil computation engine. It does a bunch of stencil computations. And then we do domain decomposition. So we have to do halo exchange. So stencil computation is followed by halo exchange, followed by stencil computation, followed by halo exchange, et cetera, depending on the type of problem you're trying to solve. And at the end of this, it updates your memory and your wave fields and models. And then before we go to the next steps, we store these snapshots and then go to the next iteration. The whole cycle repeats where you have the models being fed into the engine, halo exchange happening, more compute. And then the cycle repeats, right? You update your wave fields, some models, depending on the type of problem you're solving, and you continue doing this. So there are clearly three things which are most important for us, which is stencil computation, which is the core compute, halo exchange, where you're talking between different nodes, between different ranks, and this snapshot storing mechanism. Where do we store it? Do we store it in NVMe kind of places, or do we use memory to store it, right? Like all of these become important criteria for us to test. And we have mini apps for each and every of these components. Stencils, we have separate mini apps which do different kinds of stencil computations. We have mini apps that do just halo exchange, and we look at the network, the interconnect performance. And we have mini apps that are going to look at the memory transfer. And then we have permutation combinations of these mini apps which do stencil plus halo plus transfer to see whether we can truly hide all of these I/O behind stencil plus halo, etc. Now, why is it important for us to run different mini apps in different purchase cycles? That is because the bottleneck keeps changing. One of our principals at ExxonMobil, they like to call us as the bottleneck chasers. Like our bottlenecks are always changing. In one generation, one component is the bottleneck. In another generation, some other component is the bottleneck. So we cannot keep giving the same amount of weightage to each and every mini app from one purchase cycle to another because the bottleneck has shifted. So now, if I were to always consider compute as the king and always say that whichever hardware does well on compute, I might be actually buying a system which is streaming fast on compute, but then it doesn't matter because it's waiting forever in doing halo exchange or I/O. So it's important for me to understand where do I give my weightage. For example, when we were in 2021, most of the time was spent doing stencils, right? 60% approximately of the time was doing stencil computation. About 20% was spent doing halo exchange, and the rest is the remaining 20%. Things changed in 2024. We don't spend as much time doing stencils. We spend about 30-35% time doing stencils. The rest of the time, we're doing halo exchange, and I/O is also becoming kind of significant. So when we did our benchmarking in 2021, at that time, we were giving a lot of importance to stencil mini apps. We would say that whoever does best on stencil mini apps, we are going to consider them. But as we started approaching towards 2024, and you clearly know what happened, we moved from CPUs to GPUs, and the compute started streaming, but halo exchange was not keeping up. We started seeing that halo exchange was now becoming a bottleneck for us. So as we moved towards 2024, when we were doing benchmarking, we started looking at the interconnect as well. We started looking at how fast can data move between nodes. And also I/O is starting to become kind of a bottleneck. We're not able to hide it behind compute and and halo exchange. So we are also starting to pay a little more attention to I/O, and we are like, okay, can you completely hide it? If not, then maybe we are going to start penalizing you when we make a purchase decision. So that's the kind of methodology that we have. The methodology is we have these mini apps which target different components, and in different times, we focus on different components and give different weightages to all of these components. And then whenever we look at an interesting option, or if we are in a purchase cycle where the business is asking us, okay, what are the options out there and which one do you want to buy? One of the most important constraints for us is availability, because a hardware might be really interesting to us, but if the business comes to us and says, this year we want to buy something, we want to increase our capacity from X to 2X or 3X or 4X, at that particular point, it becomes important for us to see if that hardware is even available, right? We might have been doing benchmarking with a lot of vendors, But then if that hardware is not available within our purchase cycle, or if that hardware is not available with the cloud vendors, if we want to go there, then it's of no use to us. Yes, we will continue doing benchmarking, and yes, they'll be considered for the next purchase, but in this particular purchase cycle, this hardware is not important to us. There was a graphic that I wanted to show, which I couldn't. We generally have roadmaps of the hardware that is going to be available with the different cloud vendors, with our different integrators, and the times when they are going to be available. And if the purchase decision is from the business on, well, we need to make a purchase now, then we refer to that and we say, okay, these hardwares are not an option at all, but the other ones are. On the other hand, if it is us making a proposal to the business saying, oh, by the way, there's an interesting hardware coming out in 2025, then that availability study is kind of moot because we already know that, yeah, this hardware is going to be available and we really want to grab that hardware and use it to accelerate some of our workflows. So availability is one of our basic constraints. The next constraint is something you've heard a lot of times today, power. Our data center does not have infinite power. Our data center has a maximum amount of power, and generally, we have machines that are running in our data center all the time. So if we have to make a new purchase decision, we will have to retire some of our older machines and make space. Or we would have already retired some machine and there will be some space available. Before every purchase decision, we kind of have an idea of how much power is available in our data center. So in this chart that I've shown, it's again a very, it's not a representative chart, it's just an example. Let's assume that I have 2.5 megawatt of power available in my data center, and I have a requirement to go to, let's say, NX power. So if I have to go to NX power, and if I have 2.5 megawatt available, then performance per watt becomes really important to me. There might be a chip that's giving us awesome performance, but it is not power efficient, and within 2.5 megawatts, I might not be able to procure that chip to go to NX power capacity. So unfortunately, that hardware is of no interest to me. And in this particular representative example, H1 through H4 is all going to be not considered for the next step in the purchase decision because they don't meet my power requirement. They're not going to give me NX capacity within the power that is available to me in the data center. So performance per watt is very important to me. So one of the things that we have introduced in our shop, and this is probably an Exxon nomenclature, we call performance as BOG pips, and it's just a fancy way of saying flops, because we're doing finite difference-based stencil computations. So, BOG pips is nothing but billion of grid points processed per second. So, it's a cool way. So we always say that we want to achieve a certain level of BOG pips per watt. If you don't meet that BOG pips per watt, we're not going to consider you at all. And then comes the biggest constraint, which is cost. So all of the hardware that has passed the screening test so far, and in this example, H5 through H10, they are then taken through the cost analysis. And we are going to look at what is the BOG pips per dollar. So we generally have, X million capex to go for a new machine or a new capability. And we want to see where do we get the maximum amount of BOG pips. But one of the most important things that I have realized after having gone through many purchases and a multiple benchmarking exercise is performance per dollar is an important metric, but that is not the only metric that we consider when we make a purchase decision. Sometimes we are willing to pay a little more dollars for certain other benefits that we get. For example, if H9 here, which gives the maximum BOG pips per dollar, is not as power efficient as H8, maybe I'll go with H8 because H8 is going to unlock certain power capability of mine for my next purchase. And my next purchase could happen maybe next year. So I would want to have that opportunity to expand if possible. So performance per dollar, while very important for us as an important constraint, it is not the only constraint that we consider at the end when we make a purchase decision. So we generally create an evaluation matrix, and in that evaluation matrix, we give weightage to performance per dollar, weightage to performance per watt, weightage to cost of change. For example, if you're going from one hardware type to another hardware type, and it involves a big cost of change, maybe even if it gives us the maximum performance, we might not consider it because we might want that machine to start working as soon as we have it available on our floor. So purchasing a new hardware at ExxonMobil is quite a complicated process, and we can make a purchase decision at any point in time, which is why this benchmarking exercise becomes really, really important for us, and which is why we keep benchmarking all the time, and we are on the lookout for cool technologies. And one such benchmarking exercise led to the procurement of Discovery 5, which we are very proud of, and I think we've spoken about it in the last 2 conferences here. Steve Mariani, who's my friend, who's probably somewhere there in the audience, he spoke about our journey from CPUs to GPUs in 2022. I spoke about some things we did on Discovery 5 last year. But this machine is probably the smallest machine in terms of the space that it takes on our data center, but it is by far the fastest machine that we've had on our floor. And I would credit our benchmarking process for having recognized that it is time to move to GPUs. We did not start benchmarking GPUs in 2020 or 2021. We started benchmarking GPUs way back in 2014. And we realized that this was the time for us to go to GPUs, and it proved to be quite an important decision, and it has unlocked a lot of potential for our geoscientists. So in conclusion, if there is one message that I want to tell our friends here in the audience, it is benchmarking is not something that you should be doing only when you're ready to make a purchase. Benchmarking is something that you should dedicate throughout the life cycle of your HPC. You should always be on the lookout, because you never know when technology matures and when it is time to go. And we use mini apps. Mini apps has proved to be really useful for us. These are single, simple, standalone tools which we can share with vendors. They can optimize these and share it with us, and we can take the learnings, then use it on our own code base and optimize the code base. It is a really good way of collaborating with vendors. We have a bunch of really interesting collaborations with our vendors, which is ongoing. Even now, when we are probably out of a purchase window, we're still benchmarking, we're still talking to vendors and looking at, okay, what's the next interesting thing, what can we do, how can we optimize, etc. One advantage of a mini app that I've not spoken to you about is it really is useful for us throughout the life cycle of a machine, because every time we make an upgrade, we run these mini apps to make sure that the upgrade was successful before we try to recompile the whole application, which would take weeks, sometimes months. So mini apps have been really useful for us, and yeah, we're proud of our mini apps. That's it. Thank you.
Thank you, Karthik. I think we should have done the overflow room down into the sponsors area. I think they get good value out of understanding the complexity of these procurements and how much goes into them. And sometimes it can be frustrating to know where things are and why decisions are being made. But thanks for opening up and sharing that. So we're on time. We have a few minutes for questions. I'll bring you the mic.
So these benchmarks are run by the vendor, right?
Sometimes by the vendors, sometimes by us.
Can you share with us the way the vendors go back to you with the results? So it's just like a tarball with raw data for you to analyze later?
So as I said initially, for us, from the HPC space, we are not interested in the correctness of the data. So all that we really care about is flops, or bog pips as we call them. We are initially, the first screening for us is just performance. How fast are you? Like if we give you like a simulator mini app, how fast are you? That's all. And compare it against our existing benchmarks.
So the result is just a number, right?
The result is just a number, yeah. And then once we are interested in that hardware, that's when we go and do the correctness testing, right? So this lets us do benchmarking more often and much faster because we don't care about correctness.
Thank you, Karthik, for your presentation. This question is from an operations geophysics standpoint. So back in the late 90s, the seismic data used to be acquired using significant amount of racks in those dog houses. And then it was transferred all to software. So my question to you is, do you envision having HPC being solved using software?
HPC being solved using software?
Yeah, so back in those days, all the racks were converted into software applications, and then the doghouses became just computers to acquire the seismic data. So I'm asking you, have you thought about solving your HPC hardware quest using software?
Oh, HPC hardware quest using software. I actually don't know how to answer your question, to be honest. I think we are using software to figure out whether the hardware is good or not. Like, we have a certain amount of software that we want to run on it, and all of the benchmarking is done using software, I guess. So probably we are already using software to, look for the next generation of hardware.
Thank you, Karthik. About these mini apps, you said you give apps that have different mathematics to. Are they designed the apps such that the different mathematics would have the same computational cost between the correct and the
So we have mini apps for VTI physics, we have mini apps for TTI physics, we have mini apps for acoustic VTI, isotropic VTI, we would have mini apps for, RTM separately, we would have something for FWI separately. So all of these things are there. So that's why I said I have mini app 1, 2, 10, 15, 21. So, people here know the numbers. Some of the vendors who work with us know the numbers. They correspond to a particular type of physics, a particular type of simulator engine that we have. We don't reveal what it is to the vendors, but we know. We have a clear map. Okay, simulator mini app 2 corresponds to this simulator's, this workflow. And then if, let's say, the interest of the business is to run an N simulator, we would go and look at the map of that on N mini app, and we would say, does this mini app do well on that hardware? Because this is what they want to run, right? So we have that map. It's a one-to-one map. So that's why I said this is not an exercise that we've done in 1 or 2 years. This is a generational effort that has been going on, and these mini apps have existed, and we've just gone on adding to it and improving it.